Okay, so let's start the class. Rest all the students can join uh, later. So today's topic, we are going to check the testing of the goodness of fit. So this is one of the very important topic in statistical inference. And from this particular topic, one question is 100% sure for your examination. So from previous four topics, you may have any choices that some question may come from which particular hypothesis testing, but from testing of goodness of fit using chi-square method, one problem will be 100% sure from that. So anyway, so we will see slowly. It's a very small topic, but very important as well. So chi-square method, chi-square is generally denoted with the notation called as chi-square. All right. So the chi-square method is generally used to test the goodness of fit, basically. Test of goodness of fit. So what is this test of goodness of fit means about? Okay. For example, let's say you may have given a certain data set. Okay, you may have certain data given, and you will be having x values, and you will be having the corresponding frequency values. So let's say your x value is 1, 2, 3, 4, and 5, and let's say up to 6 I will go. And the corresponding frequencies means, let's say this x is the example that when you roll a dice, so number 1 to 6 appears on the face. So when you do this experiment, let's say up to 200, let's say 25 times, or up to whatever the number of times. So how many number of times one appear on the dice, that frequency will be given to you. Let's say uh, some random, let's say maybe 21 time one appears. Okay, then let's say one time two appears, 22, 23, 24, 25, and 0. Let's say. So how many number of times the number 1, 2, 3 up to 6 of the dice appears, represented with the frequency Fi. Now they may ask you to calculate, or they want to ask you to check the goodness of the fit. Okay, they want to check you to find the goodness of fit if the distribution is from, let's say, binomial, or maybe Poisson, or any other distribution. We have seen so many distributions in previous chapters. So if binomial, they may give you that this particular distribution falls into binomial category, or this kind of distribution may fall in the Poisson category, and so on. What you have to do is, this is the observed frequency in the experiment that dice has rolled 25 times. So based on this distribution, what they give, so as you know that your distribution of binomial written as ncx p power of x q power of n minus x, and x values are given to you from 1 to 6. Based on this p of x, we will calculate the observed frequency, which I represent with OI, or in general I will represent this with EI also. Okay. So when you calculate this EI using the distribution given in the problem, for the different x values given in the data set, you may see that you may get E1, because 1, 2, 3, 4, 5, and 6 theoretical frequencies, or the observed frequency has been given. We are now calculating the theoretical frequencies here, or expected frequencies, using binomial. So when you take n value as 5 here, because 1, 2, 3, 4, 5, sorry, 6 here. So when you take n value as 6cx, p value we have to calculate. P is the probability of getting number on the dice, so you know that the probability will be 1 by 6 because it is has 6 faces. So whenever you toss a dice, the probability of getting any one number is 1 by 6 power x. So 1 minus 1 by 6 is the q value. So 1 minus 1 by 6 is q value, and then you will be having 6 minus x. So this distribution you should use, and then you have to multiply this with 100. So you will start getting your expected frequency from E1. So E1 is the frequency when you put x equals to 1 here. Then you will get expected frequency E2 when you put x value as 2 here. X value is given, so you will get another value. So these values are called as your expected frequencies. So here two concepts are important. One is that your theoretical frequencies, which will be given most of the time. So we have to find the expected frequencies. We will find the expected frequency, and now based on this expected frequency and fi, I will calculate the chi-square with the formula of summation of fi minus ei whole square divided by summation of, or sorry, divided by ei. We will use this set of formula to calculate the chi-score. We can say this as we seen earlier that t score, z score, this will be chi-square score. Now once you have calculated this based on this set of data, that is your fi and ei, then you have to compare this chi-square value, whatever you have get, by the chi-square critical value. So as we know that whenever we want to find a critical value, we will have some kind of degree of freedom. So in this case, we will have n minus 1 degree of freedom. So for example, let's say you have got a chi-square value as 16, for instance, that's 16.5. You have fi, you have calculated ei, both you have calculated, you have used the formula. I once again write the formula. This is summation of fi minus ei whole square divided by ei. By using this formula, you have got some value. Now we have to find the chi-score value. Chi-score value you have to calculate depend upon some alpha, which is let's say 5% level of significance, and the degree of freedom is n minus 1. So this value we will calculate from the table of chi-square. So till now we have seen Z table, or we say that normal table. Yes, we have seen normal distribution table. Till now we have seen T distribution table, and now in when we have done the variance problem, we have also seen F distribution table, right? So now I am introducing you the chi-square distribution table. So this chi-square distribution table will help us to get the critical value of chi-score. Critical value of chi-square critical, I can put here. This is the critical value. So now when we have both these values here, and we will have some value. If you just compare this value of chi-square, and if it found greater than the chi-square critical, if it is greater, then we say fitness is not good. It's a not good fit. It's not a good fit. Or also we can say the hypothesis got rejected. Both the same meaning. Hypothesis rejected. Whereas if your chi-square value is less than the chi-square critical value, then either you say you have a good fit, whatever you are fitting the data using the distribution given, or we have to accept the hypothesis. Whenever I say reject hypothesis, it is always the null hypothesis I'm talking about. So this is all the introduction about the chi-square distribution. So let's see what is all its definition and all, right? So the chi-square is used to test if a sample data come from a population of a specific distribution. As I said, the distribution they will give you, that what kind of distribution you have to use to find the expected frequencies. All right. So the chi-square test for the hypothesis becomes in this manner. Your null hypothesis becomes that the data follows a specified distribution. If they mention the distribution is a binomial, then your hypothesis of alternate, your null hypothesis becomes that yes, the data follows binomial distribution automatically. Then your alternative hypothesis becomes that data does not follow the specified distribution. Specified means this will be specified to you in the problem, that what kind of distribution we have to use to find the expected frequencies. So now based on the chi-square formula, okay, because we have to run the test so that either H naught has to be accepted or H1 has to be accepted, we have to run a test. So for that, we have a formula for chi-square, which I have told you just now. This will be your Fi minus Ei whole square divided by Ei. So Fi is the observed frequency. Observed frequency means, in general, they will do the experiment for, let's say, 100 times. Okay. So in that 100 times, whatever the values you will get, that frequency is the Fi. So this frequency will be given to us. If it is not given, we can even find that. I will show you in the problem how we'll do that. And Ei is represented as expected frequency, which we will calculate based on the distribution. This has to be calculated. This we have to calculate by using a distribution, the given distribution. Though this distribution can be binomial, might be, as I just now told you. This distribution can be given as Poisson, all right, or this distribution can be given as uniform or whatever the maybe the term. Okay, but majority of the time we will only work for binomial and Poisson distribution only. But you can work out this for any kind of distribution we have seen in previous chapters. So I hope this is clear to you now. So as I've mentioned, if the value of the chi-square is the greater than chi-square critical value, here the degree of freedom is n minus 1. Standard degree of freedom we have taken. Then we have to reject the hypothesis. If it is greater, always remember, whenever it is greater, we have to reject the hypothesis. If it is lesser, then you have to accept the hypothesis. Okay. Now, in this case, your n value is the summation of Fi. We will see all these terms in problem itself. Don't look at this m is equal to 1. Okay. I will just strike out this particular statement because this is more complicated. So just forget these two statements for a time being. Just don't look at this statement. Right. Just cut this down. So only up to here you remember. All right. So we have to calculate chi-square value. We have to find the chi-critical value with n minus 1 degree of freedom. That's all. All right. Now this is the chi-square distribution table, standard table we have given. So here you can see your degree of freedoms are given here. This is your degree of freedom, and this is the critical value at 5% or 1% of level of significance. The values are given here. All right. So let's move on to the problem, and we will see how this works. So directly I jump to the problem, because when we work out the problem, then only we will see how this chi-square distribution works exactly. So let's say what they say. In 200 toss of coin, 118 head and 82 tails were observed. Okay. Now test the hypothesis that the coin is fair at 5% and 1% level of significance. All right. So they have already given you the total number of toss, which is 200. They have done this test. In that 200 run of tossing a coin, 118 times they have got head and 82 times they have got tail. All right. So when you add this both 118 plus 82, you will get anyway 200. So you can see here your F1 and F2 value they have already given. What is F1 and F2 value? It was a observed frequency. So observed frequency F1 and F2 they have already given to us. Now we have to test the hypothesis that the coin is fair. Because they are getting more head and less tail, so they are having a doubt that the coin which they are using to toss 200 times is unfair. So they want us to check the hypothesis that the coin is fair or not. So to do that, first you have to check your observed frequency of the head and tail. So F1 is 118 and F2 is 82. They have given. All right. Now, if you just add the F1 and F2, you will get 200, which is our number of tosses. So now in this case, make sure that when you decide your null hypothesis, whatever they have mentioned here, the coin is fair. You have to check whether the coin is fair. The same statement, you take it as a null hypothesis. If you want to check whether the coin is fair, then coin is fair itself is your null hypothesis. Then your alternative hypothesis become coin is not fair. So now we will perform a test on null hypothesis. So when you have to perform a test on null hypothesis, it means if coin should be a fair, I will write here, if coin is fair, it means it is a normal coin. Then if you toss the coin one time, so if you toss the coin one time, then the probability of getting head is also 1 by 2 in one time I'm talking about, and your probability of getting tail is also half. All right, so you have equal chance of getting head and tail if the coin is fair, because you are doing test on null hypothesis. All right, so that is why I have taken that probability of getting a head in a toss is 1 by 2, which I have taken as PI, or probability of ith. Ith means the 200 toss. I'm talking in general. So in a toss, 1 by 2 is the probability of getting a head, because it's a fair coin. We are doing a test on null hypothesis here. All right. So your expected frequencies now have to be calculated. So I will calculate the expected frequency. We have a formula that n into pi. Okay. So n is 200. Already we have here. And pi is the 1 by 2, the probability. So when we do that, your E1 becomes 200 into 1 by 2, which is 100. Then your E2 is 200 into 1 by 2, which is also 100. So now you can see you have got E1 and E2. F1 and F2 was given to you. F1 was 118 and your F2 was 82. So this was the observed frequency. So based on this observed frequency, we have now calculated the expected frequency, which was, we have got 100, and E2 also we have got 100. So now these two data we have got it. So now we can use our chi-square formula, which is Fi minus Ei whole square by Ei. So because we have two frequencies, so this will become F1 minus E1 whole square by E1 plus F2 minus E2 whole square by E2. Just put the values down there. So when you put the value, 118 minus 100 whole square by 100 and so on, you can see you have got the value 6.48. So now I want to find the chi-square critical value. I want to find the chi-square critical value. So how to find the chi-square critical value? We have to test the hypothesis on 5%. We have to test the hypothesis at 1% also. And degree of freedom is n minus 1. So what is the n minus 1 degree of freedom means? Then what will be your n minus 1 degree of freedom? You count here how many frequencies pair you have taken. Here you have taken 1 and here is the second, so 1 and 2, so your degree of freedom becomes 2 minus 1, which is 1. Just check this, count this particular, that how many pairs you have taken here. So this is first pair, this is the second pair. Just count that in general. So if you have two pairs, just put 2 minus 1 equal to 1. So 1 is the degree of freedom. So let us check the value of chi-square critical at 0.05 and 1 is the degree of freedom. So this value we have to check from table. So let us quickly go to the table. So we have 0.05 here and we have 0.01 and degree of freedom is 1. So for 0.05 the value is 3.84 and for 1% the value is 6.64. So we will write both the values, 3.84 and 6.64. So this will be 3.34 and chi-square at 1% level of significance and 1 degree of freedom is 6.64. So now we have got both the values. Now we have to compare the chi-square value, which is 6.48, with these two values. So now we can check here that your 6.48 value is greater than 3.34 and your 6.48 value is lesser than 6.64. So 3.34 is the critical value for 5%. So you have to reject the hypothesis H naught because it is greater, and here it is less because 6.64 is for 1%. So we have to accept the hypothesis H naught because 1% is more accurate because you are telling this with 99% confidence. So this hypothesis will hold true compared to this one. So basically overall I can claim that your coin is fair even though if you are getting more head and less tail in 200 and in 200 toss. All right, so the same thing I have mentioned here. So your degree of freedom is 2 minus 1, chi-square value is 3.84 and 6.64. So you can see for 5% we have rejected the hypothesis and for 1% we accept the hypothesis. So for 5% you are telling that your coin is unfair with 95% confidence, and with 99% confidence you are telling that your coin is fair. So overall I will claim that your coin is fair. So I hope this problem is clear. If any doubt comes anywhere, just tell me. Okay, let's see another example. We have 8 dice thrown 60 times and a frequency distribution for a number appearing on a face is given by. So here x is the number appearing on the face and here is the frequency. So frequency means this is your fi. Okay, what is fi? The observed frequency in the experiment. This is your observed frequency. So I will just write that here. This is the observed frequency fi. So you can see that in 60 time throwing out dice, 1 appears 15 times, 2 appears 6 times, 3 appears 4 times, and so on. 6 appears 17 times. So when you add all these frequencies, this should be equal to 60 because 60 times you are tossing the coin. All right, that is clear. So now we have to test the hypothesis that the die is unbiased. So now we have to, based on this experiment and the frequencies what we have got in the experiment, you want to check whether the dice you might have used is fair dice or unfair dice. So it is unbiased or biased dice. So because we are testing the hypothesis of die is unbiased, so this itself becomes your null hypothesis. So null hypothesis will be that die is unbiased, and your alternative hypothesis become die is not unbiased. So you know that we always run the hypothesis test on H naught. So we'll perform test on H naught. So don't forget that if you performing the test on H naught, in which your dice is unbiased, means it is fair. It's a very much fair dice. So if the die has to be unbiased, then if it is fair dice and you throw the dice one time, then all the number 1 to 6 have equal chance of occurring, right? So then your probability of getting a number become 1 by 6, which I have taken as pi, same as the previous examples. Probability you have to find in this case. So because it is an unbiased dice, so probability is 1 by 6. All the 6 numbers have equal chance of occurring. So now we have to calculate the expected frequencies. So expected frequencies will be now how many you will get? 1, 2, 3, 4, 5, and 6. So now you can see E1, E2, E3, E4, E5, and E6 all will be n is 60 because 60 times have tossed into the probability 1 by 6. So you will get the value 10. This 10 is same for all E1 to E6. So what is happening here now? You have got your expected frequencies as 10, 10, 10, 10, 10, and 10. All right. So this is your Fi and this is your Ei frequencies. Now you can see there's a lot of difference between observed frequency and the expected frequencies. You can see here. For one, your observed frequency is 15, whereas the expected frequency is 10. For number two, your observed frequency is 6 in the experiment, but expected frequency is 10, and so on. So now we will run the test and check whether the dice is fair or unfair. All right. So to do that, we need to have our chi-square distribution formula. So summation of Fi minus Ei whole square by Ei. So I values from 1 to 6. Just put the summation value. So when we put all the values, F1 will be your 15. This will be 15 minus 10 whole square divided by 15. Next will be your 6 minus 10 because Fi is 6 and E1 is 10 by 10. Sorry, this will be 10 only. Then F3 will be your 4 minus 10 whole square. This is also whole square divided by 10 and so on. So when you calculate all this, we have got the chi-square value as 13.6. So now we have to, now in this case you see they have not mentioned the significance level, that whether you have to test with 5% or we have to test with 1%. If they never mention the significance level, then standard you have to test for both 5% and 1%, only for chi-square distribution. So we will check for both 5% and 1%. So let us see your degree of freedom. How many degree? What is degree of freedom now? How many pairs you have? 6 pair. 1, 2, 3, 4, 5, and 6. You have 6 pair taken. So 6 minus 1 will be your degree of freedom. All right. So degree of freedom will be 6 minus 1 is 5. So now you can calculate the chi-square critical value for 5% and at 1% from the table. So we can quickly check whether it is 11.07 and 15.09 or not. Your degree of freedom is 5. So just check, we will check quickly. so that we can understand the table. All right, so here your degree of freedom is 5, and you can see at 5% the value is 11.07, and at 1% it is 15.09. So the value is correctly we have taken. Yeah. So now you can see that your chi-square value 13.6 is less than 11.07. It means you have to accept the hypothesis H naught for 5% level of significance. You have to accept the hypothesis because it is less than. Whereas, sorry, it is greater. So you have to reject the hypothesis. Whereas the 13.6 is lesser than 15.09. So it means you have to accept the hypothesis for 1%. So because 1% means 99% confidence, so you can say that your dice is totally fair. This is what I have written here. So for 5% we are rejecting the hypothesis, and for 1% we are accepting the hypothesis. The conclusion I have not written, you write the conclusion at the end. Always we should write the conclusion that the die is fair overall with 99% confidence. Why 99% confidence? Because it is accepted at 1% level of significance. Alright, so this is what I was talking about previously. So fit a binomial distribution for the following data. Now you can see the specified distribution is given to you, that fit a binomial distribution. They have done some kind of test. What kind of test they have done, they have not mentioned, but they have given the value of x and the observed frequency. Now we have to test the goodness of fit at 5% level of significance. So to test the goodness of fit, your null hypothesis becomes, what will your null hypothesis you have to take? The fit is good. Or in another word, we can say the whatever the data they have taken, this data belongs to binomial distribution. This is what we have seen in the introduction. So the data belongs to binomial distribution, and or we can say the fit is good because the distribution is mentioned over there. So to do that, I need Fi value already is there. I just need to calculate the Ei values, the expected frequencies. So how you will calculate the expected frequency? To calculate the expected frequency, you have to use the binomial distribution. All right. So what is the binomial distribution P of x? As I told you, it will be your NCx, P power of x, and Q power of n minus x. This is the binomial distribution. So when you want to calculate the frequency, you have to multiply this with 100. Okay. So let us see step by step how we'll perform that. Why we are multiplying this with 100? Because when you add all this term from 2 to 8, and you take 2 plus 14 plus 20 plus 34 plus 22, the sum is getting 100. That is why we are multiplying the binomial distribution with 100. Okay. Next, what is the mean of this distribution? You know the general formula, Fi 2 into 0 divided by 100 plus 1 into 14 divided by 100, and so on. So when you calculate the mean, I will get 284 by 100. I will calculate the mean. This will be 2 into 0, right? Uh, Plus 1 into 14 plus 2 into 20 plus and so on. Similarly, the last term will be 5 into 8 whole divided by summation of fi. So when we do that, we will get the numerator value as 284. So it means the mean of this distribution is 2.84. But what is the mean formula of binomial distribution? The mean is equal to n into p, right? We have seen that. So that implies your mean value is 2.84 is equal to n into p. I need p value, which is probability. So p becomes 2.84 by n. Then what is n value you will take? Now here is the catch. Don't count from 1, 2, 3, 4, 5 and 6 in this case. No, n value will be the last digit, 5. So n will be 5 in this case. So when you divide that, you will get p value as 0.568. So now you can use your binomial distribution formula. We have got the p value. Then your q value will be 1 minus p, which is 0.568. You have to calculate that. I don't know whether it is approximately 0.43 something you may get. So when you substitute that here, your n value is 5, as I've told you. Okay, n value is 5 because the last digit starting from 0. So 0, 1, 2, 3, 4, and 5. N value is 5 here. So 5cx p power of x, and then q value is 1 minus 0.568, which is 0.432. You can see here, power 5 minus x. So to calculate your expected frequency, you have to multiply this whole probability with 100, the frequencies, the number of times the frequencies coming, the sum of frequencies you have to multiply, right? So now the first even, if you want to calculate the x values, whatever they have given here, that x values we will substitute in the binomial distribution formula, and we will calculate the expected frequency. So first x value is 0. So put 0 in this formula. So you can see it will become 5c0 0.568 power 0, and for this power 5 minus 0. So when you calculate this, you will get 1.505. Next, E2 will be your x value is 1. So now you have to substitute 1 here in this formula. I will put this as equation number 1. So put x equal to 1 in equation number 1. So 5c1 0.568 power 1, 0.432, 5 minus 1. So you will get 10.4512. So like that, we will calculate all the expected frequencies of the different x values. So next x value is 2, next x value is 3, next x value is 4, and next x value is 5. All these values substitute in equation 1 and calculate. So now you can see here that for every x values, the observed frequency, anyway these frequencies are given in the problem. Now I have written the expected frequencies down below. And if you compare these two, you can see there is a lot of difference between the observed frequency and the expected frequency for a certain data which they have given. There's a lot of difference over there. So actually we have one more method to simplify this part, but I am not want to confuse you, so I will go ahead with the simple standard form which we have seen till now. So we'll directly calculate chi-square, which is fi minus ei whole square by ei. So this will be 2 minus 1.505 whole square by 1.505. So I have written the direct values. Okay, you know how to calculate that, and I've showed you this previously. So the value which I have got here is 3.5054. So we are testing this at 5% level of significance, and the degree of freedom is how much? What will degree of freedom? How many pairs you have taken? 1 pair, 2 pair, 3, 4, 5, and 6. So 6 pair means 6 minus 1, 5 degree of freedom we have to take. Don't count, because n value we have taken as 5 in this case. So don't write 5 minus 1 as 4 degree of freedom. Just check the pairs, how many pairs you have taken. This is some uh, good way to identify the correct degree of freedom. All right. So with this degree of freedom, you have the value 11.070. If your degree of freedom you take wrong, then this value also becomes wrong. So degree of freedom you please take carefully. So now you can see that your 3.505, which is a chi-square value, is lesser than 11.070 because it is less. So you have to accept the hypothesis H naught. And what is the hypothesis we have taken? That the fit is good. So you have to claim that the fit is good fit. It's a good fit. Which fit we are talking about? This expected frequencies. The fit which we have taken here is a good fit at 5% level of significance. If it is good at 5%, then obviously that will be good for 1% level of significance also. So this is all about the chi-square distribution. They may give you the similar data. Okay, I just wanted to tell you here only. They may give you this similar data, for example, same data, but apart from binomial, they may give to fit a Poisson distribution also. So to do that, till here the method will be same. The only part will change is the binomial distribution mean. So what is the mean of Poisson distribution? Can anyone tell me? The Poisson distribution is nothing but your m power of x e power of minus m divided by x factorial. Then what will be the mean of Poisson? That is nothing but your m. But you need p value. So if you just go back to the previous classes, you can see that we have used Poisson, we have used binomial distribution itself to find the mean of Poisson distribution. So in this case also, this formula retains same even for the Poisson distribution, because Poisson is the what we can say, it's a different case of binomial distribution when your n goes extremely large. Okay, so anyway, we'll speak about Poisson distribution a bit later. So till now, if any doubt here, then you can just ask me. So all the three types of the problem we have covered almost. So if anyone has any set of doubts in this class, then tell me. Next class we will see some more problems of different types of chi-square distribution. All right. So this is all about today's class. Still, two more topics has been pending for this chapter. One is the test of independence. Test of independence is pending, and as we have done the test on correlation, we want to do the test of regression coefficient. This two topic has been pending, which I will cover in upcoming class. All right. I don't know who has framed the syllabus. There's a lot of test of hypothesis they have included in your syllabus. But anyway, this is all about